Today I have with me Dr. Michael McKubre. Dr. McKubre is an accomplished electrochemist who has been working in the field of cold fusion for over 20 years. He joined Stanford Research Institute in the late 1970s and served as their Director of Energy Research up till present day. He has made countless contributions to the field, including important replications in the mid-1990s that demonstrated an important correlation between excess heat and helium production in a variety of experimental setups. In 2009, he was interviewed for and prominently featured in the 60-minute segment Cold Fusion is Hot Again, in which the successes of cold fusion over the past 20 years were brought into focus. Dr. McKubre, thank you for being with me today.
You're very welcome.
So, can you elaborate a bit more about your background, your credentials, and your entry into the LENR field?
Sure. I was trained as an electrochemist. I actually started my undergraduate work in the US at George Washington University in Washington, D.C., and spent a couple of years there, went back to New Zealand, where my family was from, finished up my bachelor's, master's, and PhD in electrochemistry at Victoria University, Wellington, New Zealand. When I came to do a postdoctoral fellowship, the number one school of electrochemistry in the English-speaking world is the University of Southampton in England. It was that because of the presence of Martin Fleischmann, who I knew by reputation to that point. And so I went to spend 2 years in England working for Sir Graham Hills, who was head of the chemistry department at Southampton. But the principal department in chemistry was the electrochemistry department headed by Professor Martin Fleischmann. So I got to see a lot of Martin. I knew him very well. I understood him to be probably the brightest and most able experimentalist that I'd met in my career up to that time or since. So I had intermittent contact with Martin over the years. I left Southampton in 1978, joined SRI, and I've been at SRI now 35 years, the only place I've ever worked, starting as an electrochemist, as program manager of electrochemistry for a while, and when cold fusion came on, it was just a natural thing for me and my group to get involved in this idea of Martin's. What I've said before is that had it been anybody else other than Martin Fleischmann, I probably wouldn't have bothered to rise up out of my chair and move into the laboratory to test it. The idea of it seemed so unlikely at the time, and for something like a decade before March 23rd, 1989, in fact, since my arrival at SRI in November of 1978, I've been working on the deuterium-palladium system. We developed a hydrogen sensor to measure the concentration of dissolved hydrogen gas in the cores of, in the coolant systems of conventional nuclear reactor systems. We happened to be testing that device in the CANDU reactors. The Canadian reactors are heavy water-based, so I had a decade of experience with deuterium and palladium before I ever heard of the cold fusion announcement of Fleischmann and Pons. So my group was well-equipped, well-established, well-set. I knew the players, I knew the tools, I understood how to load deuterium into palladium. I understood the kinetic techniques of electrochemistry that you needed to do that, and we had already in hand a technique for measuring the extent of loading, just by means of the resistance ratio. So the first thing that my group did really to contribute to the development and advancement of the field was to properly quantify the calibration of the resistance ratio versus loading function in the extremely high loading regime that was clearly going to be necessary before anything as unexpected as a nuclear effect would be found in the deuterium-palladium system.
Can you talk a bit about the work that went into correlating helium production with excess heat production?
Yes, well, the first thing we started out to do was to check out whether Martin was right or not. We gave it about a 50-50 shot, again, only because it was Martin. Anybody else I'd have given a much lower probability, but we set up some experiments as carefully as we could to interrogate the hypothesis that a nuclear level heat effect can be seen in the deuterium-palladium system when deuterium is loaded to a sufficient degree into palladium. We knew it had to be the high loading regime because none of these effects had been observed before, and the palladium deuterium system was well investigated in the low loading regime. So we tried to design an experiment that we could get this palladium as loaded as possible. Low temperature, solubility increases with decreasing temperature. High pressure, solubility increases with increasing pressure. And as high electrochemical current density as we could achieve in a safe apparatus. So we took us about 2 months of just thinking, head scratching and thinking, to design a calorimeter that would give us an unambiguous and conservative result under the conditions that we were seeking to test, high loading. So we had a result by about June, perhaps late June of 1989, so April, May, June, 3 months we spent thinking about the experiment, setting it up, and about a month operating it. And we had a result which confirmed our hypothesis. There was, in fact, a heat effect that could not be accounted for by chemistry, and that set us thinking about what should we do next. The two things to do next, obviously, were build a better calorimeter. At that point, I was not very experienced with calorimetry. None of my group was. So we set out to design a modern calorimeter that would give us conservative results under all conceivable operating conditions. So by the time we'd set up our second, now mass flow calorimeter, we had the ability to produce, not on every occasion, but in about a third of the experiments, we were able to produce a heat effect that was very clearly not of chemical origin. It didn't look very nuclear either, in that the expectation that had been visited on us by, I think in part, malicious particle physicists, but they took the word fusion to mean hot fusion, of course, and fusion is a reserved term in the nuclear physics world. When you say fusion, you're supposed to be talking about one and only one reaction, possibly two. Reaction between deuterium and deuterium to produce neutrons and tritium. And the reaction between deuterium and tritium also may be used, the word fusion may be used, but both cases hot fusion, both cases energetic products. In neither case could these reactions explain what was being observed. We were seeing the heat consistent with nuclear reaction, but we were not seeing neutrons. We were interrogating the system for neutrons. All of our experiments have always had radiation health safety level of neutron detection. Although neutrons have been seen in some of these experiments, we've never seen them, and they're certainly not present commensurate with the heat. If they were, Fleischmann, Pons, all other successful experimenters in this area and their students would be irradiated. It would be obvious. So whatever it is obviously not hot fusion, as Julian Schrenger pointed out. What is the product? We measured for tritium. On occasions we have seen tritium, but in no case have we seen tritium commensurate with the heat. There's some tritium, and a single atom of tritium produced from a chemical reaction would be highly anomalous and possibly worthy of a Nobel Prize. So we've seen 10 to the 17th tritium atoms produced in our experiments, no Nobel Prize. But that's still not enough to account for the heat. The heat has to be produced in a reaction that gives a non-radiative and non-energetic particle or product. Otherwise, we'd simply have seen it. That leaves you with very few choices. There are some transmutation choices at higher atomic masses, but the most logical and obvious and almost the thermodynamically necessary consequence of a reaction between two deuterons is helium-4. And if you were to take two deuterons put them away in a box until the end of time and come back in and interrogate the box, you would always find helium-4 in the box. It is the logical thermodynamic product of the interaction of deuterons. Problem is that it's almost impossible to do it, as Heisanger and others pointed out, in a simple pairwise reaction. It's not possible to conserve energy and angular momentum. So the deuterons will react together to produce helium-4. It's a downhill, thermodynamically downhill process, yields 24 million electron volts, which is huge. So we set out to make measurements looking for helium-4. I should point out that we were not the first to think of this or the first to do it. The first people to think of examining their experiments and looking for a correlation between helium and heat was Melvin Miles at China Lake, the Naval Weapons Center at China Lake in California. And Mel Miles, working together with Ben Bush at the University of Texas, Austin, had developed a very, very clever experiment to correlate heat with helium in the off gas from calorimetric cells. Thermodynamically open, these cells evolved their gas. They simply took gas samples and submitted them to a mass spectrometer for analysis. And I think in all, Mel Miles has run approximately 20 experiments. When there is heat, there is helium-4. When there is no heat, there is no helium-4. And a simple statistical analysis of their observations and non-observations of heat and helium gives you a probability of better than 1 part in a million that they are wrong. There's a 1,000,000 to 1 chance that they are right, simply statistically. So Mel Miles was the first to do it. It took a while for others to catch on. First thing I did was hire Ben Bush on sabbatical, actually, to SRI, and we replicated the Miles-Bush heat-helium results at SRI in the early to mid-90s. So we were able to confirm what Mel Miles had shown in 1991, 1992. By 1993, 1994, we were able to confirm that particular result in that particular mode. Then we set up to perform different types of experiments, different calorimeters, gas cells as well as electrochemical cells, to see if in fact there was a quantitative correlation between the appearance of heat and helium-4. We know how much heat should be associated with each helium-4 atom, 24 million electron volts. Now the trick is to make enough helium-4 that you can distinguish it from the background. The air that we're breathing right now, you and I in our different locations, but the air that we're breathing right now is 5.22 parts per million helium-4 in it. It's the same everywhere, all over the surface of the planet. It doesn't sound like much, but nuclear energy efficiencies, nuclear energy densities are so much greater than chemical. They're approximately 10 million times greater than chemical energy densities, and that's what makes them interesting and important. But to produce 5.22 parts per million of helium-4 in a gas sample requires the production of a lot of energy. So we had to build our experiments up, make them more robust and reliable, and make them produce more energy in order to give us some increased confidence in the search for helium-4 as a product. But we did it. By the mid-90s, mid to late 90s, we had 3 different experiments in 3 different geometries with 3 different modes of calorimetry, all displaying a correlation between the quantity and time of production of heat and helium, a temporal and quantitative correlation between the production of these 2 nominally independent products.
And as far as my understanding goes, at least 12 other groups have replicated it.
Yeah, I don't know what the total number is. There are 3 or 4 groups in Italy, 2 or 3 groups in Japan, I think a group in China, a couple of groups in the United States, probably adds up to 10 to 12. So there's been a fair amount of replication of the helium. It's not an easy experiment. It requires sensitive apparatus, requires careful isolation from the environment. So you need to do a very good job of keeping your cell helium leak tight. And helium is the leakiest gas known to man. It's the hardest gas of all to trap. So you have to know what you're doing, and you have to spend money. And the mass spectrometer that we have to do this job was bought for us by DARPA, the Defense Advanced Research Projects Agency, and it's in an initial cost $350,000, installed cost about $1 million, including all of the maintenance and technician care. So you're in a $500,000 to $1 million range before you can even begin to play this game. That's why there haven't been more replications.
Now, when we start with deuterium as a fuel and we end up with helium as a product, that doesn't necessarily shed light on the mechanism. Is that correct?
That's correct. I think we got the beginning point, we got the end point. It's like thermodynamics. You know what your starting material is, you know what your final material is, but you know the reaction pathway can be many and several, and it is at this point, to me at least, unclear what the detailed mechanism is. One thing is for sure, it is not a simple pairwise interaction of two deuterons to produce a helium-4. If the only thing in this process were two deuterium atoms, my hypothetical two deuterium atoms in a box stuck away until the end of time, it would take until the end of time to produce this reaction. The rates are simply not there, and the products are not the right products. So we know, actually we knew from the very beginning that this was always made, you know, as some sort of revelation or mystery that fusion was supposed to occur in one particular form and one form only, and that we should expect to see neutrons and we should expect to see tritium. We always searched for them, but we didn't expect to see them, at least not in quantitative correlation to the heat. Had they been there in sufficient quantities, the experiment would have told us very clearly it would have been dangerous. So the mechanism unclear. A number of people are working on mechanistic ideas. It has to be, in my view, a many-body quantum coherent process. There has to be many participant species. And two deuterons ultimately do give their souls up to become a helium-4. I do believe that that is the most likely explanation. But I know it doesn't happen as a reaction solely between two deuterons.
Perhaps we'll come back to theory a little bit later. For now, I'd like to ask about what led up to the 2004 Department of Energy review, the work that went into that, and ultimately what was the outcome?
Yeah, we had a very good conference organized by my good friend Peter Hagelstein in 2003 in Cambridge, Massachusetts, associated with MIT. And Peter works at MIT. So we had ICCF 10, the 10th International Conference on Cold Fusion. Peter, being an academic, had set very high academic standards, and that was a particularly solid conference technically. The energetics folks showed up and spoke for the first time. It was sort of very, very well selected papers for, you know, academic motivation. High quality papers, high quality presenters, lots of new stuff, lots of good stuff. So that conference proceedings is a particularly valuable one just because of the pre-selection. But I didn't know who it was, but somebody from DOE or somebody associated with DOE, or maybe one of the MIT folks, was sufficiently impressed by the conference, by the presentations, quality of the information being presented, to get that information back to the top folk at DOE. DOE was also approached directly by Peter, saying that it's Peter Hagelstein saying it's time for a review. And one of the guys that we had ultimately in the review was politically connected to a former boss of DOE. So we made a three-pronged approach, and DOE was very responsive. They invited us first to a phone conversation and then down there to set up the review. The review was organized pretty much by Peter Hagelstein and I. There are other names on the review paper, but pretty much all of the writing and organization was done by Peter Hagelstein and I. Peter was taking a sabbatical, actually. He took a 6-month sabbatical, or a summer anyway, sabbatical at SRI. And we were planning to do all sorts of experiments, but we got sidetracked by this DOE review. So we spent the entire summer poring over the literature, discussing this with our colleagues, figuring out what information to contain, and putting the whole thing together. The review was conducted in 2 parts. There were direct presentations to a subset of the review panel, and then the materials that we wrote and recommended were intended to be read by reviewers who were not physically present on the day of the presentation. It was quite remarkable, actually. So one of the more interesting days of my life. The review went very well. We walked into a room of largely skeptical, some hostile, some friendly, but certainly very cautious group of reviewers that DOE had selected together, and made a series of presentations. By the end of the day, we had pretty much convinced the attending reviewers that there was something of very great significance. We were being congratulated. I remember one of the senior reviewers, who was also on the first ERAB panel report, coming up to me afterwards and saying, "I had no idea how much the field had progressed, and congratulations. We thought this was all very good." Unfortunately, the politics were not done at that point. The reviewers who were present were, I think, uniformly positive. A lot of the reviewers who had not been present for our day of presentations, who had merely read the material, or in some cases, I'm certain, did not read the material. Some of them came back with fairly negative, some irrationally negative comments. And the synthesis that was put together by DOE at the political level read more or less the same as the synthetic view of the first ERAB panel report. You know, a fraction of our members, of the reviewers, believe there is something here. I think a third of them believed in the heat, a third of them believed in the nuclear evidence, and a third of them didn't believe in anything. So we had certainly a split field. But of the people who physically attended, I would say pretty much every one of them was convinced that there was either a nuclear effect on the basis of heat or a nuclear effect on the basis of nuclear products. But the words that came back from DOE is the review panel is mixed. Some regard the evidence as clear and convincing. There is scope for well-designed research projects in this area submitted to DOE through the normal review process. All very well and good and right, actually. That's the correct thing. That is the exactly correct way of analyzing the situation. There looks like there's something here. In order to understand it better, we need to do more research. They encouraged collaboration, particularly with the national labs. Well, DOE sort of runs the national labs, so that's reasonable, or expected anyway. The only problem with that whole process was that in order to get anything new funded out of DOE in a zero-sum game, you're going to have to displace an existing project. They didn't provide a new program manager or new funds to handle the influx of proposals. The proposals were thrown into the normal review stream, and no special encouragement, I think, was given to funding these over any other initiative. In fact, it was stated explicitly that should be given no more weight than any other submission. So the consequence of that is the same as the consequence of the first ERAB review, although requests for proposals were, if not solicited, at least permitted. These requests for proposals weren't given any special pathway towards funding, also explicitly, and no funded proposals resulted from that activity. I know a number of submissions and a number of rejections. I know of one submission and acceptance of a cold fusion proposal to and by DOE, where the money was taken back after it had been allocated simply because it was cold fusion. So pretty much politics as usual.
I did read in a Washington Post article that, at the very least, it raised morale to a certain degree. Would that be correct?
The field picked up. I congratulate DOE. I congratulate the higher level folks who managed to push this through and get the review undertaken. The fact that DOE is paying attention is good. It's actually also their job. I mean, that's what they should be doing, but it is good to see clear evidence that they are doing their job. Even better evidence would be to accept, well-formulated proposals, and it may just be that there haven't been, well enough conceived and constructed proposals for DOE to pick them up. That might be the answer. I've never submitted a proposal to DOE on this topic.
Now, over the last 20 years or so, how, in your view, has skepticism evolved, if it has, or do you still hear the same objections that you did in 1989, 1990?
Yeah, a lot of the critics are really, really stuck in 1989 and refuse to learn. A very prominent critic whose name I won't mention, but closely associated with the American Physical Society, one of my colleagues attempted to put in his hands a paper that would rebut whatever argument he just made. He said that this isn't so or this is so, and he tried to put in his hands a paper which, if read, would clarify the situation and negate the concerns that he was uttering, but he refused to accept the paper. He would not allow it to be put in his hands. He let the paper drop on the floor rather than touch it. This is the level of hostility. This is the emotional base for the hostility. And for some, that hasn't changed. What has changed, of course, is that just as we're getting older, so are our critics, and some of the early critics are just not operational anymore. They're too old, and some of them have died. So the cry is taken up by younger crowds to some extent. You can't measure helium in the presence of D2, mismeasurement of input power, and just sort of nonsense things. I think that the people who say these, mouth these criticisms are aware that they're nonsense, but they need to sow the seeds of doubts in people that don't think as clearly as they do, or we do. So, I won't believe that you have produced energy until you can boil me water for a cup of tea, was Douglas Morrison's cry. As I pointed out on the 60 Minutes piece, in one experiment alone, we produced enough hot water to make 1,500 cups of tea. We didn't choose to make 1,500 cups of tea. That's stupid. That's not scientific. All we need to do is measure the energy and allocate that energy to a particular process. But energy on the scale of tea making has certainly appeared in these experiments. But that criticism still comes up. People still say it. People are not aware of the fact that hundreds of megajoules of excess energy have been produced in these experiments over quite long periods of time. But the energy is very, very significant. Garwin on 60 Minutes says, I don't think McKubre manages to correctly measure his input power. Well, power is the easiest thing to measure, and the meter in your home measures power accurately. Otherwise, the utility companies would be either cheating you or cheating themselves. We know how to measure current, voltage, resistance, time. These are things we can easily measure. So if there is a problem with these experiments, it's certainly not in the measurement of input power. So I think it would be reasonable to argue that the critics have not evolved their arguments in a very sophisticated way. They haven't kept up with the evidence as it's been produced. In some ways, we're holding all the aces. We've done the work, we've done the calculations, we've spent the time, we've spent the energy and the brain cycles to think this thing through. The people that work in this field are not stupid. They're not, on the whole, self-deluded, and they're a very capable set of individuals. amongst the best group of people that I've ever worked with in my life. And the experimentalists that have stuck with this are extremely capable individuals who are well aware of the issues that the critics bring up. We're aware of them before the critics brought them up. But the fact that these questions are raised, in public means that they have to be efficiently rebutted. And that's a difficult thing to do, particularly for a non-technical audience.
Rob Duncan of the University of Missouri is somebody I have a lot of respect for because he started off as a skeptic, but he was willing to engage with the material. He was convinced by the material, and so convinced that he organized the 2009 symposium, and I'm sure he was critical in getting ICCF 18 over at the University of Missouri.
Absolutely. Absolutely. Rob is unique, as far as I can tell. When we were thinking about how the 60 Minutes piece would be put together, the CBS guys knew that a critic was needed. The argument couldn't be made simply between advocates, people on my side, or even the traditional critics of old whose positions were entrenched. What we needed was a new face, somebody to take a new look at the material and make an honest judgment publicly about what he saw and how he evaluated the evidence of the experiments. It was, I think, our fifth attempt that we found Rob. We were able to find physicists, some with household names, who were willing to take the money and willing to do the job, but were not willing to read the materials or travel to see an experiment. They knew what their opinion was. They were prepared to stand up on camera and state their opinion as fact without the effort of going through the physical materials, the literature, or looking at the experiment. So the 60 Minutes guys said, well, thank you very much. We'll keep you in the file, but that isn't what they were looking for. But surprisingly large number of quite prestigious individuals were willing to make that public statement without evaluating the evidence. Rob was special. Rob was willing to read through the materials, capable of understanding them. He has a background in calorimetry, which makes him very special indeed. That's very rare in physics. He was president or chairman of the American Physical Society Measurements Standards Committee. Exactly the right job. He knew how to make measurements. Had a background with experimentation of his own. And he was not only a calorimetrist, but had experience with National Instruments, which was what the energetics folks in Israel were using. So he was willing to jump on an airplane, fly to Israel, spend a week evaluating the experiment, talking to the researchers, pounding the table, asking hard questions. At the end of that time, he was converted from being a skeptic, more than a skeptic. He was sort of hostile, and his expectation was that there was nothing there. And he told me later he used to make jokes about cold fusion. But he had sufficiently open mind that having been exposed to the evidence and persuaded by it, he was willing to change his mind. It's unfortunately rare. And even rarer, having changed his mind, he was willing to speak about it publicly. I think that makes Rob unique. I've forgotten who it was who was searching with a lamp for one honest man. Well, we searched with our lamp and we found one honest physicist, and that's Rob Duncan.
That transitions nicely into my next question. Could you give us a little bit of an overview of Irving Dardich's work at Energetics in Israel, what they're doing there, and what their results have been?
Sure. Well, I spoke before about the conference in Cambridge, Massachusetts, ICCF 10 in 2003. And I was exposed for the first time to the work of energetics. I'd seen the guys around. They'd showed up to a previous conference but not said anything. This was the first time they opened their mouths and said something in public. And I was with Martin Fleischman there. He happened to leave the room at the time of the energetics presentation. He came back afterwards and asked me, what did I miss? I said, you missed the best paper of the conference. And these guys came after a year or less of experimentation of their own and were producing results that were superior to anything that the rest of us were discussing at that meeting. So energetics came out of nowhere and produced better results than anybody in the field. People, such as myself with a decade or so in the field at that point more. It was 2003, so I'd been in it for 14 years. These guys were already doing something that I didn't understand and couldn't do myself, producing levels of excess heat and consistency of heat production that were far beyond anything that I was capable of doing. And also, they were able to load reliably to very high levels deuterium into palladium, and I knew how hard that was. So I was fascinated by energetics, and I immediately invited myself to visit their sponsor, a man called Sidney Kimmel, who made his money in the garment business, but philanthropist, good man, good vision. So I invited myself to see Sidney Kimmel and basically said to him, how can I help? What these guys are doing is highly important. I'd like to become associated with their activity and contribute in any way that I can. And I said that three possibilities, on the basis of the results that are produced by energetics in Israel, either they had divine guidance, or there is something to what Irving Dardick is saying, or maybe a combination of the two. But clearly what it was that energetics had that was different from everybody else, and in my view what it was that made them successful, far more successful than anybody else, was this crazy waveform that Irv dreamed up called a superwave, a highly variable waveform containing a number of modalities. It has a wide range of frequencies and a wide range of amplitudes. So as a good electrochemist, I already understood that the best way to load deuterium or hydrogen into palladium was a constant, steady, direct current DC experiment controlled situation. Certainly not with a wild and crazy cyclic waveform. And furthermore, I wasn't expecting a medical doctor to be able to inform me in my own field of expertise. However, I was open-minded enough, and I'd seen the results. So I wanted to understand what a superwave was, how it worked, and how I could use it in my own experiments. So I got to know Dr. Dardick, I got to know Sidney Kimmel, I got to know the energetics folks in Israel. I visited there 3 times. And still am amazed at the potency of the superwave driving function to both load hydrogen or deuterium into palladium and other metals, and to allow a fluctuation of the loading levels, which is associated with the flux, the movement of deuterium or hydrogen across the interface. And by that time, by 1995, in fact, I'd understood that the excess heat effect has a number of preconditions, 2 of which are to obtain and to maintain a very high loading ratio and to have a high flux of deuterium through the interface. The problem between 1995 and 2003 was I did not know what waveform to use that would allow me to simultaneously obtain high loadings and a high interfacial deuterium flux. You can have a high flux condition, but what usually happens, and it happens in every case for the waveforms that I've tried, is you lose more on the downside than you gain on the upside. And you tend to deload your electrodes, so though you can get the deuterium moving backwards and forwards through the interface, you lose more when it leaves than you gain when it returns. It's a partially reversible process. The only waveform I know to this day that is able to get you a high flux and high loading condition is Irv Dardick's superwave. So, while I don't understand it fully, I have complete empirical confidence in the waveform and its effects. And I propose to spend quite a lot more time studying that very waveform in various systems.
What kind of output were they getting from their cells compared to more conventional approaches?
Well, famous result obtained in 2005-ish and introduced at the ICCF conference in Marseille, was experiment 64, energetics 64. Experiment 64, in the first 17 hours, the input power was 40 kilojoules, 40,000 joules. The output was 1.04 megajoules. So there is something like 25 times more energy coming out of that experiment than had been put into it. I don't think that number has been replicated by anybody, in fact, other than energetics. They boiled water, so you have 25 times energy gain and boiling water. If you could produce a water heater with those characteristics, you get 25 times more hot water than the electricity that you pay for, and you can boil water with it. You would have a product immediately. And the only thing that would prevent you from having a product is A, that you couldn't do it on demand, which we still can't, and B, that it required bulk palladium, which is expensive. But the characteristics that they demonstrated in that experiment and a follow-on experiment a few days later and some later replications, the features that they demonstrate are already a product. That is productizable, if you can use that word.
And they have pretty high reproducibility rates, is that correct? I've heard 80% quoted. I don't know if that is usual.
We set up, and this experiment was so important, 64, that I went to my sponsors at DARPA and said, we have to understand more about this. We want to replicate it. I got a fairly considerable amount of money for both energetics and SRI to replicate the energetic 64 result or get something like it. We weren't aiming for 25 times power gain, 2,500%. We were aiming for 200-300%. We thought it was a sufficient level to be convincing. So we set up a series of experiments. I think there were 23 or 24 experiments in all. Like 17 of those experiments produced excess energy, not at the 300% level. Some did. Most of them lesser levels, 30, 40, 50, 60, 70, 80% in some of the experiments, but all of them well beyond the measurement uncertainty. So that 17 out of 23, let's call it something like 73%, is the most successful series of experiments that we had performed at SRI up to that time, and the highest level of replicability that I'm aware of in an electrochemical, Fleischmann-Pons heat effect type experiment. But of course, even 70%, 75% that's not enough. If you're going to commercialize, you've got to get closer to 99.99%. People would be very dissatisfied with their cars or their water heaters, for that matter, if a quarter of the time you turned it on and you didn't get anything out of it. So we have to get better.
Speaking of commercialization, we have three major companies on the horizon. So there's Rossi, Leonardo Corp., and you have Brillouin here in the States, and you have Defcalion, who's in Canada and I think Greece. So do you have anything to say about who you think might be furthest ahead, best in a position to get to the market first?
I don't know. I don't know. I don't have any inside information for Rossi or Defcalion. I do have inside information for Brillouin, which means that I can't talk to you about it. But I don't think first matters. I mean, the field is so huge. If anybody gets to the marketplace, there will be a position to set up and establish a giant corporation that will be larger than anything that any of these guys can imagine. There's room for all three of them to succeed and 20 more people to succeed. It's like automobile manufacturing. How many auto manufacturers are there in the world? 100 maybe. And 20 or 30 big guys, all of them competing for a very large market very profitably. So I would like to think that Brillouin, Defcalion, Rossi, and Piantelli, who is the father of that line of thinking, all could succeed beyond their wildest expectations. Rossi is to be credited for some things. I mean, he's a different sort of guy, not a scientist in the mode that I'm most familiar with, but he did pick up on the idea of Piantelli's that the nickel light hydrogen system or nickel natural hydrogen system was capable of producing meaningful levels of excess energy. This is something that Piantelli had spoken about and written about as early as 1992, 1993. I think he has patents extending back to 1993. We didn't really believe it at the time. That we spent all of this work with our deuterium, scrupulously avoiding protium, hydrogen, and using hydrogen or light water or normal water as our calorimetric blanks. So the idea that you could perform this experiment equally well with normal water as heavy water was first a surprise. Nickel itself is not so much of a surprise, and nickel is poor man's palladium. It sits above it in the periodic table. It has very similar chemistry and metallurgy. The significant difference between nickel and palladium is that diffusion coefficient of hydrogen isotopes in palladium is 2 or 3 orders of magnitude higher than it is in nickel. So large objects, big cathodes like Martin Fleischmann's 1 centimeter cubed, he was able to load his 1 centimeter cubed in a month or two. It would probably take 10,000 years to load that same thing with if the cube were a nickel. So nickel is a problem, but only if it's large. Small dimension structures should work just as well with nickel as with palladium. The problem that most of us in the field, the traditionalists in the cold fusion world, had was the hydrogen, the protium, rather than the deuterium. Now, it's true that you can react 2 H's to produce a D. That's where all D in the universe comes from. And that is an exothermic reaction. That is downhill, and you can make the same argument I made for deuterium and the helium. This is the thermodynamically obvious and logical necessary consequence of the reaction of 2 protons, but it's a very difficult reaction. It happens under very, very extreme conditions. It's hard to get that reaction to go in the sun. So to get an HH reaction going is something that most of us believed, and some still believe, to be not possible. I think if my present thinking, the way that I can hand wave that away is that Brillouin, Defcali, and Rossi, Piantelli are not looking at HH reactions, although Brillouin certainly believe they are, but looking at HD reactions. So it's this 1 part in 6,000 deuterium in normal water which is providing the reactive species. It's a stretch intellectually, it's a stretch technically, and hasn't been proven experimentally, but that's my hand-waving way of massaging away the sore point of proton-proton reactions. But as with the conventional Fleischmann-Pons heat effect, mechanism unknown. We know something about the reactants. Deuterium seems to help. Protons might work. So that's 2 things we know about the reactants. We know something about the products. Helium-4 has been seen, absolutely certainly. Helium-3 has been seen, absolutely certainly. Tritium has been seen, absolutely certainly. So we have nuclear products, in fact, the very products of fusion reactions, but the mechanism by which these products come into existence has been described by probably 30 theorists in possibly 100 different theories. None of them self-consistent. None of them, well, they're not the group is not self-consistent. And most of these theories, as Ed Storms likes to point out, most of these theories are not even consistent with the experimental facts that we have available to us. So it'll be a while before theory catches up with experiment. This is not the fault of theory. This is the fault of experiment. We experimentalists have simply not provided with the theorists with a clear enough set of input and output conditions for the theorists to be able to be certain what it is that happens and what are those things that don't happen.
Now, we have preconditions that are necessary for the reactions to start, and then, of course, there's the mechanism itself. Somewhere in between those two, I see Storm's nuclear active environment theory. which is nanocracks at the surface, may be coming into play, and if not nanocracks, perhaps some kind of surface defect that might be assisting with the reactions. Do you see any validity in that idea?
I go along with Ed to the point of acknowledging the existence of a nuclear active environment. The place that this reaction, whatever it is, takes place is not normally present and not everywhere present in the metallic lattice. A special condition needs to be created in order to facilitate this reaction. That's why it takes such a long time. In bulk palladium materials, it takes hundreds of hours before the reaction occurs, even after my preconditions are established. The loading is there, the flux is there, the current density is present, everything is that I say is necessary is there. It still takes 300 hours for a 3 millimeter diameter palladium cathode to produce the effect. What is going on? What is going on is a reconfiguration of the lattice. And it's a reconfiguration close to the surface, or maybe at the surface. Just the very fact that the helium, or at least half of it, pops out immediately into the gas phase for analysis tells you that the reaction is very close to the surface, within trapping distance of helium from the surface. So a special condition is created at or near, adjacent to the surface. We'll call that a nuclear active environment. I'm good with that. Whether that nuclear active environment is nanocracks and what, and the rest of Ed's theory chain holds up, that it is a linear array of DD or HHH polymeric structures. It's an interesting idea. I like the idea. It might be. I have no direct experimental evidence that that is so, and we need to set out to test that experimentally. If cracks, what size cracks? If we get the right size crack, then the effect should scale as the quantity of those cracks scale. So make more cracks, you get more heat. Nobody has been able to set up experiments to directly test that hypothesis. So it remains a hypothesis. It needs to be tested. If it turns out that Ed is right on this, then my hat is off to him. It's already off to him. He's done probably more work than anybody in the field and has done a better job of codifying the information that's available. So Ed is already a cold fusion hero. If it turns out that his NAE is a system of microcracks, nanocracks, and that the nuclear mechanism is along the lines of what he describes, then he will absolutely be a candidate for the Nobel Prize that Martin Fleischmann can't get because he's dead. The field deserves a Nobel Prize. Somebody should get it. If Ed turns out to be right with his NA and nanocracks, then he should certainly get it, and I'll promote him for it.
With the few minutes we have left, maybe you can illuminate us about your future plans or current projects you're working on.
Sure. We, for years and years and many years, we tried to science this thing into existence, do experiments, good experiments, write up papers, present them to the peer-reviewed journals for publication and discussion. That didn't work. It didn't work. That process became derailed by the critics in their attempt to shut the field down. One of the attempts to shut the field down was to prevent publication. If you can prevent publication, you can prevent young academics or people with the pretension to be academic from getting involved in the field. Publish or perish. If you can't publish, you can't get promoted, you can't be an academic. Very effective, very cynical activity on the part of a fairly small but prestigious group of individuals to just kill the field. I still don't know why they did it. So we weren't able to science this thing into existence. The continuity of funding was not available, and the availability of conventional publication sources and presentation sources were not there. We created our own conference, we created our own journal. Still not enough. You can't get academics involved, so we don't have the horsepower. So you can't science this thing into existence with the establishment hostility that exists today. We tried to use the NASA approach, appeal to the public, play to the gallery. The 60 Minutes piece was part of that attempt to go directly to the people and say, look, we don't know what there is here, but there's something here, and that something has to do with energy, and the energy that is produced is a whole lot more benign than the energy that we're presently using to supply the world. Get people to write their congressmen for support. It worked a little bit, but not completely. The third path that we have to get the Martin Fleischmann's discovery accepted by the mainstream science establishment and mainstream science journals is by making a product that does something you can put on the table. Just do it. Go ahead, make something, make heat, make lightning, I don't care. Make something that's useful. Make tritium, which I don't want to do, but we do know how to do. So I'm looking to commercialize this activity in existence. So for the remaining years of my career, I've moved my attention away from the pure science side and towards the supporting commercialization activities side. And I don't care who wins. As I said before, Brillouin, Defcalian, Rossi, Piantelli on the nickel light hydrogen stuff. I can see why nickel, I can see why normal hydrogen, they're cheaper and more plentiful, have engineering potential. If any of them succeed, if all of them succeed, great. We can then go back to the physics community and say, look, we're producing commercial heat. We're boiling thousands of people's water for cups of tea and whatever. At that point, when it's unequivocally evident that commercial objects can be made, the attitude of the hostility will dissipate. So I'm looking forward to some sort of commercialization activity. It doesn't even have to be very good or very large or very successful, but the fact of a commercial object is going to change the discussion.
All right, Dr. McKubre, thank you so much. I think this has been a really interesting conversation. I appreciate your time today.
Thanks, John. Get back to if you have any questions or queries or any clarification needed.
All right, thank you very much. Will do. Take care.